Please look at the figure. By convention, a magnetic field out of the page is represented with dots, while a magnetic field into the page is represented with crosses. Last lecture, we discussed the definition of a magnetic field, which shows the relationship between a field and a field force. We have known that the magnetic force acting on the charged particle moving in the magnetic field is perpendicular to the particle's velocity, and consequently, the magnetic force does no work on the particle. Now consider a special case. A positively charged particle is moving in a uniform magnetic field. The initial velocity is perpendicular to the field. The direction of the magnetic field is into the page as shown in the figure. In this case, let's analyze the motion of the particle in the field. To determine the motion, firstly we should analyze the net force on the particle. The magnetic force on the particle equals V cross B times Q. The magnitude of the force is QVB because the angle between V and B is 90 degrees and sine theta equals 1. Based on the right-hand rule, the direction of the force is always perpendicular to the velocity. Thus, the particle is moving in the vertical. As shown in the figure, the rotation is counterclockwise for a positive charge in a magnetic field directed into the page. We use the particle under a net force model to write Newton's second law for the particle. Because the particle moves in a circle, we also model it as a particle in a uniform circular motion, and we replace the acceleration with centripetal acceleration. FB just provide the centripetal acceleration. Based on Newton's second law, so we have this equation, QVB equals mv squared divided by r. We solve for radius r of the circle as expressed by this equation. From this expression, we can see that the radius of the path is proportional to the linear momentum mv of the particle and inversely proportional to the magnitude of the charge on the particle and to the magnitude of the magnetic field. The angular speed of the particle equals v over r. The period of the motion is equal to the circumference of the circle divided by the speed of the particle. These results show that the angular speed of the particle and the period of the circular motion don't depend on the speed of the particle or on the radius of the orbit. This principle is used in the application of a type of accelerator called cyclotron. Let me give you a more general case. A charged particle moves in a uniform magnetic field, but its velocity is at some arbitrary angle with the field B. What about its motion? As shown in the figure, if the field is directed in the x direction, there is no component of the force along the x direction. As a result, the x component of the acceleration must be 0, and the x component of velocity remains constant. So, the charged particle is in equilibrium in this direction. However, the magnetic force causes the components Vy and Vz to change in time, and the resulting motion is a helix whose axis is parallel to the magnetic field. If we view along the x-axis, a circular motion of the particle is observed. If charged particle moves in a non-uniform magnetic field, the motion is complex. For example, a magnetic field is drawn at the two ends and weak in the middle region as shown in the figure. Under the action of the magnetic force, the charged particles would spiral repeatedly from one end to the other and back. This configuration is called a magnetic bottle because charged particles can be trapped within the field. In many applications, the charged particles experience both a magnetic field and electric field. For example, if a charged particle is moving with a velocity v in the presence of both an electric field E and a magnetic field B, the net force acting on this particle equals the vector sum of the electric force QE and the magnetic force V cross B times Q, as expressed by this one. Based on this equation, we have some applications such as velocity selector. We could have the charges with the same velocity by applying a combination of electric field and a magnetic field oriented as shown in this figure. A uniform electric field is directed to the right, and a uniform magnetic field is applied in the direction perpendicular to the electric field which is into the page. If Q is positive, the velocity V is upward. We could determine the magnetic force by the equation QV cross B. The magnitude of FB equals QVB since the velocity is perpendicular to the field. The direction of FB is determined by the right-hand rule, which is to the left. On the other hand, the value of the electric force equals QE, and the direction is to the right. When the magnitudes of the two fields are chosen so that QE equals QVB, the two forces cancel. In this situation, V equals E divided by B. The charged particle is now modeled as a particle in equilibrium and moves in a straight vertical line through the region of the fields. We find only those particles with this speed will be able to move in a straight line. We call this configuration velocity selector. A velocity selector can be applied in a device called mass spectrometer. It can be used to separate ions according to the mass-to-charge ratio. Please look at this configuration. The charged particle with the speed of E over B is moving in a straight line, passing through a velocity selector and entering a second uniform magnetic field, B0, which is directed into the page. Upon entering the second magnetic field, under the action of the magnetic field only, the particles move in a circular path of radius r and strike a detector array finally. Applying this equation, R equals mv divided by QB0, we can express the mass-to-charge ratio by this one. Therefore, the radius R varies with mass-to-charge ratio of the particles. Now, let me show you another application, cyclotron. A cyclotron is a device that is used to accelerate charged particles to very high speeds. The energetic particles produced are used to bombard atomic nuclei and thereby produce reactions. A schematic diagram of a cyclotron is shown here. We could see two semicircular containers with the D shapes, which we call Ds. A high-frequency alternating voltage is applied to the Ds. A uniform magnetic field is directed perpendicular to the electric field. Because the Ds are made of metal, the region inside the Ds is field-free because the electric field is shared by the container. Thus, the charged particles in the Ds experience only the magnetic force and move in a circular path. Consider a positive particle is released at P near the center of the magnet in 1D. Suppose uppercase T represents the time interval for a particle required to complete one revolution in 2Ds. So the particle arrives at the gap in a time interval half of T through a semicircle drawn by the dashed black line. Now, the key point here, the frequency of the applied potential difference is adjusted so that the polarity of the Ds is reversed in the same time interval with 1/2 of t. That means after the particle travels around 1D and reaches the gap, the polarity of the D is reversed. For example, if the applied potential difference is adjusted such that D1 is at a lower electric potential than D2 by amount of delta V, the particle accelerates across the gap to D1 and its kinetic energy increases by amount of Q delta V. It then moves around D1 in a semicircular path. After a time interval, half of t, it arrives at the gap between the Ds. At this instant, the polarity between the Ds is reversed and the particle is accelerated again toward D2 across the gap. Therefore, for each half-circle trip around 1D, the particle will acquire additional kinetic energy of Q delta V and move in a semicircle of a larger radius. This motion repeats until the radius of the circle is approaching that of the Ds. The particle with high kinetic energy leaves the system through the exit slit finally. The operation principle of the cyclotron is that the period of the circular motion is independent of the speed of the particle, as discussed above. We understand that the charged particle in the motion would experience the magnetic force. Electric current is the net motion of the carriers in a wire. So, if a wire carrying a current is placed in a magnetic field, we would expect that the force will be exerted on the current. We'll talk about it next lecture.